So in section 4.3, not only are we going to see x and y, but we're also going to see a new variable that we really haven't seen this year, and it's the variable z. So when we have three variables, we're looking at three dimensions. So like this is like finding the point of intersection or the plane of intersection from three lines in real life. So like if you're looking around the classroom right now or looking around at home, you're looking basically for three actual lines that intersect, like three separate things. So if you're looking at the classroom, we're looking at like where the floor and the wall meet. That would be one point with two, but then you would be looking for a third dimension. The third one could be like if you're looking at a corner. The corner walls meeting the vertical line of the wall, meeting with the ground, the one side of the ground and then the other side of the ground. Those are meeting at a point, three different planes. The ground here, and then the wall meets all at a point. And if you're looking at in your bedroom right now or wherever you're completing school at home, if you're looking around, look for an area where three different lines are going to be intersecting. When we're looking at systems of equations, we're looking for those actual points mathematically where those three lines are going to intersect. That's what we're doing today. X and Y is when we just have two dimensions and we're looking at two lines intersecting on a piece of paper. But when we add the third dimension, it actually takes everything and makes it real 3D. It makes it like what you can see in real life. Like when you're an architect and you're trying to design the new house that you're flipping and you're looking for, okay, well this wall, and this wall are going to go here. Everything needs to line up perfectly, and obviously if you're building like a house, everything's going to be 90 degrees so that everything's standing up, right? But that's basically what's happening, and you could solve that mathematically to see where all of these different lines would intersect. So that's what we're going to do today. Today is really the first day of seeing something from Algebra 1 turn into Algebra 2 because now we're solving systems of equations with three variables. So you will now see not two equations, but we will be seeing three equations. And if you were struggling with the last section, now you're going to be struggling even more, which is a problem. I want you to make sure to see me if you're struggling before, because now it's going to be even more difficult because now we are going to be seeing three or more equations with three or more variables. So like I said, these three pictures here would be examples of what can happen when we have three equations. So imagine each equation being a specific plane. By plane, I mean like these rectangle boxes. So there's three of them. There's this pink one here. This, I guess we can call this like a yellow one, and then this blue one here. So this example would be a solution at one point. So three lines can intersect at exactly one point like this. Three lines can intersect at one line or one plane if you're looking at the pink one, the blue one, and the yellow one. Or they don't have a solution at all. Sometimes this might happen, especially if you're thinking about like when you have walls in a house. One wall goes this way, one wall goes this way, and one wall goes this way. All three of them will never connect, which is how they're making that inside space. So sometimes there will be no solution. There are two different methods to solving linear equations in three variables. So the first method we're going to use is called back substitution. These have to be specifically set up for us to solve them this way. And these are the easier of the two because when you're looking at your three equations, the first one, x minus 2y plus 2z equals 9. Then the second, y plus 2z equals 5, and the third, z equals 3. They give us the answer to one of the variables already. So we see three variables, x, y, and z, but I can see right here they're already telling us the answer to one of them. We already know the answer to z is 3. Every system of equations with three variables are going to have three answers. So the point, instead of just being x comma y, it's going to be x comma y comma z. I know that my answer to the last part of this ordered pair is going to be 3. I already know because they tell me in the actual problem. We don't have to solve it at all. That makes this very, very, very simple to solve using substitution. If I know that z equals 3, look at the other two equations. You can find the variable for one of the other ones by easily substituting 3 in for that variable z and solving for another one. You're going to want to substitute that into one of the ones that will be easy to find the other one. And it's not the only method to do it. You can actually take 3 and replace it in for this z here or this z here. And you can solve, but if you're looking at these two equations, which one do you think would be easier to do, would be more beneficial for us to replace the 3 in for? The first equation or the second one?
The second one.
Yes. Why, Scott?
Because, well, first it will answer the y equals.
Exactly. Exactly.
You'll have an extra variable.
Yes. If we take the second equation, y plus 2z equals 5, and we replace 3 in for z, we will then eliminate all of the other variables except y, and we're going to be able to just get the answer. If we replace 3 for z in the first equation, we still will have 2 unknowns. Once we replace the 3 in for the z for the second one, we will only have 1 unknown, which we can easily solve for. Since 2 times 3 is 6, we're going to get y plus 6 equals 5. We can subtract both sides by 6, and we can find that y is equal to negative 1. Since 5 minus 6 is negative 1. Now we have 2/3 of our answer. Our answer is going to be something, comma, negative 1, comma, 3. Now we have z equals 3, y equals negative 1. Now it's time to solve for x. That's the only variable we have left. There's one equation we still have not used, and the only equation that has x is the first equation. So now we need to take this first equation and solve for x. The only way to do that is by replacing in what we have found for y and what we have found for z, and then solve for the missing variable. You can only solve for one unknown at a time. So x minus 2y plus 2z equals 9. I'm replacing in a negative 1 for y, so this is going to be x minus 2 times negative 1 plus 2 times 3 for z equals 9. So the rest of this is just algebra. Negative 2 times negative 1, this is going to simplify to be a plus 2, so it's going to be x plus 2 plus 2 times 3 is 6 equals 9. 2 plus 6 is 8, so we have x plus 8 equals 9, subtracting 8 from both sides. We're going to get to the missing variable for x is 1. So the solution is 1, negative 1, and 3. The last thing you should do before moving on is just verifying that your answer is correct. Like I said throughout this whole chapter so far, with systems of equations, you can verify that your answers are right if you just take the time and replace the variables and the numbers you got for those variables in, and then see if it works for all the equations. Now we have 3 equations. The first one, we're replacing a 1 in for x, a negative 1 in for y, and a 3 in for z. So this is going to be 1 minus 2 times negative 1 is negative 2, so it's going to become 1 plus 2. And then this is going to be plus 2 times 3, which is 6. So it's going to be 1 plus 2, which is 3, and then 3 plus 6 is 9. It works for the first one. For the second one, we're replacing a negative 1 in for y and a 3 for z. So this is going to be negative 1 plus 6. That equals 5. It works for the second one. And the last one is just z equals 3. There's nothing to replace in for that. So it does work for the other two, so we know that this is the final solution. Only downside about these problems is that every problem is a little bit different. There's not really one way to memorize all of the solutions. Each one you're going to have to problem solve. So if we look at the next one's similar in that one of the variables is given and they give you the actual number for that variable, but then they leave it up to you with what to do next. So what I want to do is give you guys a few minutes and try the second one on your own. They tell you x is equal to 10, so we already know 1/3 of the answer. It's going to be 10, comma, something else. But I want you to try and find y and z in whatever order makes the most sense for this specific problem. So I'm going to give you some time to problem solve and figure this out on your own first. Then we'll go over the answer as a group. right, let's go over this answer. Hopefully you had enough time to try this one on your own. These require practice. There's not going to be one time where you're going to just solve it and it's going to work out perfectly each and every time. Like even when I'm doing it, each problem that I see is new. It's not like I can look at each one confidently and be like, okay, this is how I would solve this one. Like each one you have to look at, see what you have, and then determine a plan. And it's honestly, even though this is math and you might not actually use exactly this in real life, in your everyday life now or later when you have a job, but it is honestly teaching you how to take what you have and problem solve and know that if it doesn't work the first time, you have to try something else. So for the first one, they give you that x is equal to 10. So because of that, I'm trying to then look at the other equations and see which one makes the most sense to replace 10 in for. It's not always going to be the second one. It's not always going to be the third one. It's not always going to be a certain thing. In this one, you're looking at the variables that are left. So when I look at the other two equations, the second and the third one, I would want to take this x equals 10 and replace it in, if possible, for another equation that when I do this, I will only have one variable left. So when I take the 10 and I replace it in for x, I will then be able to solve for that other variable without having to do other steps. What's the better equation to use then? The second or the third?
Second.
Yes. If I take the 10 and I replace it in for the second equation, 3x plus 2y equals 2, I then can solve for y. Because I have what 10 is equal to for x, I can take this, replace it in, and then I'll be able to solve for y because I would only have one unknown. If I chose the third equation, I would have two unknowns, and you can't solve equations with two unknowns. You can only solve for one. So 3 times 10 is 30. I get 30 plus 2y equals 2. I'm going to subtract both sides by 30 to solve for y here. I get 2y equals 2 minus 30 is negative 28. Dividing by 2, I get y equals negative 14. So I know my second part for my answer is going to be negative 14 here. I'm going to put it in my ordered pair just so I can see what I solved already and see where I'm at, where I need to go. The last thing I need to do is solve for z. So then you look at all of the equations given. The first equation isn't going to help us because it's just x equals 10. The second equation isn't going to help us because there is no z variable. The third equation is the only one we didn't use yet, and it's the only one with z. So I have to use x plus y plus 2z equals 0. Because I know x is equal to 10 and y is equal to negative 14, I would then replace what those numbers are. This is going to be 10 plus negative 14 plus 2z equals 0, and then I would be able to solve for z now that I only have one unknown. 10 plus negative 14 is negative 4. To solve for z, I'd add 4 to both sides. I get 2z equals 4, and I would divide by 2. 4 divided by 2 is 2, so I get z equals 2. So altogether, my answer is going to be 10, negative 14, and 2. And again, it really is helpful to take the time, replace these numbers in for x, y, and z, make sure they work. You'll be able to verify that they do work, and you'll know for sure if you get the right answer or not if you do take that time. So I do want to just show you so you can, oops, I don't know why I erased it, so that we can just verify that. What was the answer, 10?
10, negative 14.
Okay. So if I put 10 in for x here and negative 14 in for y, let's just verify. 3 times 10 is 30. 2 times negative 14 is negative 28. 30 plus negative 28 is 2. So that one works. The next one, 10 in for x, negative 14 in for y, and 2 for z. 10 plus negative 14 is negative 4, and 2 times 2 is 4. Since negative 4 plus 4 is 0, this one works as well, and then this one's just x equals 10. So it works for all three. We know that we can move on confidently that we got the correct answer. It only takes a couple seconds to check your work. I highly suggest doing that before moving on. Okay, here's the next method. We'll be able to do one problem together with this method and then call it a day. So method 2, our goal in method 2 is to get the system into this thing called row echelon form. So this form occurs when the system has a stair-step pattern with leading coefficients as 1. These problems are more difficult because the systems of equations that are given are not going to be easy in that there's going to be one that tells you x equals 1 or y equals 2 or z equals 5. These are what you're normally going to see. 3 equations that don't have any real great information for us. So when we have a problem like this, which is more difficult than the first problem, we will have to use this method, which basically says take the equations, figure out which ones would be good to use elimination for to eliminate variables, and then problem solve using substitution to try and figure out what to do next. There is no step-by-step. Each problem is going to be a little bit different. So I'm looking at these 3 equations, and I know the example tells us what to do, but you would want to really look at the 3 equations with the 3 variables. I see x, negative 2y, and 2z. I see negative x and a 3y, and then I see 2x minus 5y plus z. So just by looking at these really quick, I can see using like your elimination mind, you're going to want to try to eliminate a variable. And when I'm looking at these, I can see that I can quickly eliminate x in equation 1 and equation 2 if I take the 2 equations and I add them. So if I take equation 1, which is x minus 2y plus 2z equals 9, and I take the second one, negative x plus 3y equals negative 4, and I add these straight down. Notice I left a space for the z part because there is no z term, so I think it's helpful to leave that space when it's not there. If I take equation 1 and equation 2 and add them straight down, the x's are going to eliminate, which will be helpful for us. So I'm going to take negative 2y and add it to 3y. That's going to be a 1y plus 2z plus 0, z is just 2z, and 9 plus negative 4 is 5. So what I did here with this first step is I took the 2 equations, the equation 1 and equation 2, and I added them together. And I got my new equation here, which is y plus 2z equals 5. Now, that didn't really do much and help us in any way so far because I don't have an equation like y equals this or x equals that. So what we need to do is continue to problem solve. What we did was we eliminated x in the first 2 equations. And what we're going to do is now eliminate x again by taking equation 2 and equation 3 and doing some stuff to it so that x eliminates here as well. So equation 2 is negative x plus 3y equals negative 4. And equation 3 is 2x minus 5y plus z equals 10. I should leave a space here because there's no z. Now what I am going to do is eliminate x in these 2 equations as well. To do that, I will have to take this first equation and multiply everything by a number so that it will eliminate. It's not going to eliminate the way that it currently is. So I'm going to take the first equation and multiply it all by what?
2.
2, yes. I take it and multiply everything by 2. I'm doing that so that this can eliminate with this equation here. So I'm going to kind of just like draw a line here so I don't have to write everything again. I'm going to take every single term and multiply it by 2. And that first equation now turns into negative 2x. 2 times 3y is 6y. There is no z, so I'm going to leave a space, equals 2 times negative 4 is negative 8. Now I have another line that I'm drawing just to show that I'm going to take these 2 equations, I'm going to add them straight down. When I do that, the x's cancel out again. Negative 5y plus 6y is 1y. Z plus 0 z's is just z, and 10 plus negative 8 I have here too. So now I have these 2 equations, y plus 2z equals 5 and y plus z equals 2. These equations are helpful because now I have 2 equations that both have the same exact variables. Y plus 2z equals 5 and y plus z equals 2. Now we can use our elimination methods from previous sections to eliminate and solve this system of equations now that I'm down to 2 variables. I totally eliminated the third. So what I'm going to do is use elimination, and instead of adding straight down, I'm going to actually subtract, because if I subtract the first equation minus the second equation, the y's are going to cancel out. You don't always have to add, you can subtract. And because I'm using subtraction, y minus y goes away. 2z minus 1z ends up being 1z, and 5 minus 2 is equal to 3. So now after all of that, I now finally found what z is equal to. Now I know what z is equal to, I then have to look for the equations that might be helpful for me to find out the answer to another one. So I go through these equations. X minus 2y plus 2z equals 9. Negative x plus 3y equals negative 4. And 2x minus 5y plus z equals 10. So none of these ones really are helpful. So if I look down through the other ones that I already created, why don't I look at these two here? Y plus 2z equals 5 and y plus z equals 2. I can use these equations and I can then find what y is. So I went through the first three. Those are not going to be helpful. So why don't I take a look at one of these two. This one I feel like might be easier since I don't have to do any multiplication. This is going to be y plus, I know now z is equal to 3. So I replace 3 in for z. And I solve by subtracting both sides by 3. 2 minus 3 is negative 1. So now I should have this set up. I don't know x yet, but now I know y is negative 1. I know z is 3. Okay, so what I did is I took one of those other equations instead of using the beginning ones that were not helpful to me to find out what y was equal to. Now I could have used the other one. I could use this one if I wanted. I would get the same thing. 2 times 3 is 6. I'd subtract 6 from both sides, and I'm going to get negative 1 still. Now that I'm done with that, I have 2 out of the 3. Now I go back to the beginning equations because these ones that I have, they don't have any x's in them, and I need x. So choose your favorite one. The first one, the second one, or the third one. It doesn't matter, but me looking at these three, I like the first one the best because it's a positive 1x. I know that when I solve and put the numbers in, I'll just be able to get what x equals. Kind of easier than if I have to multiply it by 2 or divide it. So I'm going to go and use the very first equation. I'm going to use green just to kind of show you what I'm doing now. And I'm going to use this one, x minus 2y plus 2z equals 9. I now know that negative 1 is what y equals. So I'm going to replace in a negative 1 in for y. I now know that 3 is what z is, so I'm going to replace a 3 in for z, and then solve for x. Negative 2 times negative 1 is going to be a positive 2. It's going to simplify to be x plus 2 plus 6 equals 9. 2 plus 6 is 8. So I'm going to get here x is equal to 1. And then you could take the time, replace in your 3 numbers in for x, y, and z to verify that it equals 9, negative 4, and 10. And then you'll be happy to see that it does do that, and you'd be able to move on knowing that you got this answer correct. These problems are difficult. If you think back to what we did, we eliminated x first in both of the equations and got 2 new equations. Once we got those 2 new equations, then we could just use elimination and substitution like we would previously from the last section.